if you look at the outline here, you'll see that we've got clicking pointage example or estimate. And I'm going to give you an example of how to click or how to calculate your clicking pointage. You know, so many points out of 25 for class participation. We'll work that out. And then we'll talk about these other two concepts, kinetic energy, which we stopped just before we could get to kinetic energy last time, and then gravitational potential energy. Now, kinetic energy is going to be really nice because it will help us grapple the stopping distance brain burner in such a way that you will feel that it is not such a brain burner when you use energy instead of momentum. Here's the SI schedule, and this is one of my very, very, very favorite quotes from Martin Luther King Jr. I have a dream that my 4 little children will one day live in a nation, and they do live in a nation, they're still alive, where they will not be judged by the color of their skin, but the content of their character, which I feel is a very noble quotation from a very noble guy. Rest in peace. All right. Before we get to your clicking pointage, late breaking news, flash, there will be an SI review for exam 2 next Tuesday, 6 to 7:50. So that's almost 2 hours, and it's going to be right below us in room 106, classroom building 2. And I have another nugget of late breaking news that William, that I didn't share with the class the other day. Maybe I didn't. The students that go to at least two SI sessions prior to exam 1 finish 10 points higher on average than the students that did not go to SI. So it is very, very helpful for you. If you haven't been to SI, try to make it to the online session tonight, and then next Tuesday, the SI review. And then you have a regular Monday session, correct? Good. So repeat? All right, so you have we better go back to the previous slide. Next week, you'll have a regular Monday session and a regular Tuesday night session. And then, so right after, so that's in classroom building 1 to 12, and then right after that you dash over here to classroom building 2, room 106, for the big SI review. Okay, so that makes sense. All right, so there's a lot of SI action heading into exam 2 next Thursday, and next Thursday is nice because for many of you it is the last class before spring break. And matter of fact, I'd like to see a show of hands. Raise your hand if this is your last class before spring break. Nice. So you guys crush the exam and then have a nice vacation. All right. Now, before you do that, I want to go through an example of how to calculate your class participation pointage from clicking. That I mentioned on the syllabus. Here's the syllabus, and the way that it's the normal conditions are you actually have to be here in the room, so you can't click from home. It doesn't reach that far, and you can't be in the parking lot. It doesn't reach that far either. So you got to be here. It's got to be working. And then, of course, it has to be registered. Now, there's some of you that haven't registered in web courses yet. Still, some people with 0 participation pointage. God bless you. I've explained it about 9 million times. But if you want to know, if you still don't have your thing registered, you're getting zeros, talk to Darian in her office hours Friday, or me anytime, of course, or Miss Caroline in her office hours on Monday. Oh, there's another. To get ready for the exam, too, office hours with Darian on Friday, and with Caroline on Monday, and of course with me on Wednesday. But you've got to do this stuff. These are the basic specs for it. Now, and here's a close-up of it. Now, the participation, the 85% mark is what we consider full participation. And they just told me in the physics department, yeah, just make it 85%. And so that gives you a little bit of leeway, you know, to occasionally miss class or misplace your clicker, but not a whole lot. I mean, you still got to be here for 85% of the questions. Now, the problem is I don't ask the same number of questions every day. So, you know, like if you're going to miss, if whoever is not here today, we're going to have a bunch of clicker questions today. I mean, we're going to have about 7. So, good. But, you know, so you want to make 85% of them. And this doesn't include the clicking items on exams, though. That's graded separately. So this is just regular lecture participation. Now, if you have less than 85%, then we have to do your calculate your grade proportionally. You'll get less than 25 out of 25. And that is actually what we are going to do. Here's the pull quote. This is the money quote from the syllabus. More than 85% answered, 25 out of 25 for the semester grade. Fewer than 85% answered, we make your pointage proportional. And then I say in the syllabus, we will work out iClicker 2 pointage examples in lecture. And that is what we're going to do this morning. So here, you should be taking notes on this, by the way. And here's where we definitely need some notes. So item 3 on clicking pointage estimates. Currently, as of Tuesday, there were 21 clicker questions, and 85% of that is 17.85 questions. So you can't have a fraction of a question. So if you have 18 or more answers on the books in web courses, and you can just look at your grades page and add them up, then you'll have 20. That means you're above 85%, and you get 25 out of 25. And hey, you guys, there's buku students in here that are 18 or higher. So most of you guys are looking really righteous, okay? But it's for the students that have fewer than that, you have to work it out proportionally. Now, here's the basic proportion. Go ahead and write this down in your notes. This is going to be for the example of John Q. student. And what you do is you figure out John Q. student or your percentage, or whoever, you know, you can figure it out for a friend, and then solve this proportion and figure out how many points that corresponds to. So this is the basic proportion that you've got to work. So we're going to do some cross multiplication, stuff like that. But let's give John Q. student some actual numbers. All right, so let's say that he has answered 13 items this semester, and starting with the official start of clicking in lecture 5 and all the way up to Tuesday's lecture, lecture 13. All right, now 13 out of 21 is 0.619. Break out your calculator, you're going to need it in a minute. And if you don't have a calculator, break out your cell phone and use that calculator because you're going to need it in a minute. And so this particular student, John Q. student, his participation rate is kind of stinky, 61.9. But it's not like he's totally out to lunch. But he should be higher than this. Hopefully, not too many of you have a participation rate, 69%. But if this was you, what you would do is you'd put that 0.69 in the numerator. Melanie, was that you? Okay. I just looked around to see who was blushing the hardest. I could see who it was. Anyway, so what you do, you put, you figure out, you count up, all right, you go in grades, how many have I got answered? 13. Divide that by 21, 0.619. And then you put it in the numerator over here on the left. And then in the denominator is the 85% performance level. Now 85 is to 25 points as 0.619 is to John Q students' points. All right, so that's why the proportion is set up. So when I say you calculate it proportionally, this is what I mean. 85% is considered full participation rate. 25 points is full participation pointage. Melanie. That's separate. Early eye clicker, those are bonus points. They don't end. And because remember, we started out with a couple Chuck Norris and Bruce Lee questions, but starting with lecture 5, that's when the official clicking started. So if you have a bonus point from early registration, that's not in this category. Just think of those bonus points or any bonus points as being attached to your final exam. Everybody's going to be taking the final, except for maybe some SSG leaders, and so those bonus points never disappear. Sava, question?
Yeah, I was just wondering, so we could improve our percentage with the iClicker questions up until the end of the semester?
That is correct. Sava's asking, can we really improve our clicking percentage, our participation rate, through the rest of the semester? And the answer is yes. John Q student right here, we're not even halfway through the semester. So he's got plenty of time. There's going to be a bunch of more questions. And if you answer all of them, you're going to go somewhere between 61.9 and 100. Now, you won't have 100%, but actually all you need to do is 85%. So you could probably get that. So anyways, so there's your proportion. Now what you do is you cross multiply. And I just saw somebody in the back row over here. When I said cross multiply, they stuck out their lip, and that's all right. And here's to cross multiply. You clear the denominator on the right by multiplying both sides by 25. Okay, so that's what this is. Now, make sure you jot that down because I'm going to ask you a clicker question about John Q students clicking points in just a second. So let's see if you guys, can jot that down and then calculate it. And here we go. Okay, so you're going to have a clicker question here and break out your clicker if you haven't already. And it's really a simple question. How many points does John Q student have? With the example that we are looking at. We're on frequency BB. Let's go. And type in your answer to the nearest tenth of a point. Because I have a comment about that. Better? Better light? Okay, so remember when you're typing in your number, use the up and the down arrow keys and then hit the send key. Don't forget that. Okay, 1 minute. And hey, you guys, jot down the proportion and jot down your answer. And hopefully it'll be right. Sava and Melanie, or Sava and Megan. Is this light interfering with your taking notes? Sava, you're good? Okay, Melanie, you're good? Melanie. Megan. Yeah, you're good over there? So Megan, Sava, Alana, you're good. All right.
Good too.
What is your name again?
Jordan.
Jordan. Jordan Carson.
No.
Jordan
You probably don't know my last name.
McFly. Jordan
I
McFly.
would love that last name.
What is your last name?
Harold. Yeah, I know.
That's a reversible name. How's it?
Harold.
So are you like a spy for the FBI or? I mean, like a.
You don't
Ooh.
want to know?
Okay. All right. All right. Whoa, we're overtime. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Ching. Uh-oh. No, dude, you had like almost 3 minutes for that. Okay, most of you got it right. 90% of you got it right. And now, write down answer 18.2 out of 25. Side note, Dr. B always rounds up. So John Q. student would actually go to 19 points out of 25. All right, so I calculated this example out. I chose it very carefully to show the rounding up at the end. So don't forget that. Write down in your notes, Dr. B rounds up. I don't round to the nearest, I round to the next one up. All right, so hopefully you've done that, and whoa, my earphone just fell out. Hold on a second. And I've already calculated this for you, and it is posted in web courses. Now, this is just the pointage that you would have if Wednesday had been the end of the semester. Now, we've got a whole lot of more semester, so this is just your preliminary estimate. Here's what it looks like on the grades page. Right here, it says participation point estimate February 25th. Is that today? Yeah, okay. And that's for lectures L5 to L13, which was Tuesday lecture. All right. Now, right now you won't be able to see it because I have it on mute. But after class, I'll unmute it, and you'll be able to see what you got, and you'll be able to verify that. Do the calculation. You can do it right now. I mean, if you wanted to. And then when I unmute it, you'll be able to say, yep, I got the same answer as Dr. B. And students, one last, here's a little close-up on it. One last comment on this. And I'd like you to add this to your notes, the bottom line. And that is, you can use the similar calculation at any point in the semester. So you can do it 2 weeks from now. Now, the baseline number of questions will be different. It'll be 30-something in a couple weeks. But the percentage works the same way, and that proportion, the only thing that might change, Sava, on the proportion is your percentage. You know, the numerator on the left-hand side. Okay, so you can still use that proportion. But you might have 32 questions in a couple weeks instead of 21, the way we do right now. All right. Now, let me pause for questions. Yeah, so Sava just asked me this. So our pointage here is based on participation whether you get it right or wrong. Even if you get 0 questions right out of 3, but you've answered 3, and that is correct. It is participation. And that's why when you look at this, for instance, down here, it says L5 answers. Right below that, you can see it here, is L5 correct. All right, now the correct I use for figuring out bonus points. And you can make a side note about this. If your correct tallies up to 75% or more, then you get 4 bonus points at the end of the semester. If you, but your regular participation, something out of 25, Celine, is from L5 answers, L6 answers, L7 answers, and all the way down to the end of the semester. Okay, so you can always figure that out with a little bit of mental elbow grease and a little bit of calculation. Let's continue now, and let's talk a little bit more about energy concepts and calculations. And my promise is that once we get this comment in place, or this concept in place, the stopping distance brain burner will be considerably easier for you to wrangle and wrap up. Unlike what we did, it was very complicated last time. It was a deluxe brain burner. Okay, so last time we went over this concept where we took a very simple accelerated trajectory, a straight down free fall from rest of a basketball, for which we know the mass, we know G, so we can figure everything out and rivet it down, bolt it in place for this trajectory. And we found that for equal increments, the temporal partition for which the geometric quantity is delta t, that the dynamical quantity, momentum, comes in equal bite-sized chunks. So equal time, equal momentum. Okay, and that's the temporal partition of the vertical free fall trajectory. Fairly simple one, but it's one that Galileo would have loved. Now, the other partition that we started talking about was this one, the free fall trajectory that is now partitioned with delta y. In other words, the different tick marks on my trajectory are based on measurements with meter sticks. And I just chose delta y of 18 meters negative because it's dropping. And that's how I made my spatial partition. So this is the same trajectory, but partitioned in a different manner spatially. But the same question can be asked. Is there a dynamical quantity that comes in equal increments for this partition? In other words, is there some dynamical quantity, capital U, that has equal delta U's for equal delta Y's? All right, so basically what we're suspecting, or we're trying to figure out, is if four-dimensional space-time, time being the fourth dimension, if that's really true, then I should be able to get some dynamical concept here, or some dynamical quantity that does the same thing on this spatial partition that momentum does over on this partition. And as I mentioned last time, the answer to that question is yes. There is a dynamical quantity, and it is called energy. And so let's get back to our four-dimensional analogy with the impulse. So here we go. This is going to be a little bit detailed, so make very careful sketches as we go through this. Now, the impulse equation over here is easy to see on a temporal partition of the vertical free fall trajectory of the basketball. We know what the net force on the basketball is. It's just good old mg, 9.8 meters per second squared times the mass of the basketball. All right. So this F net up here is known. It's downward. And delta P is downward. I'm getting more and more downward momentum. And I have delta T. Now, if we kind of take an analogy, so my dynamical quantity in the impulse equation is delta P. So there's this other function, energy, for which I'm still using the capital letter U for unknown. It should behave in this way. If I make delta S a generic marker or a generic symbol for any kind of spatial displacement. So if I'm moving horizontally, instead of writing delta S, I would write delta X. Okay? If I'm moving in free fall, like free falling downward, I would use delta Y. And if I were, walking from the lectern toward the first row of seats here, that's a Z direction, I would use delta Z for that. All right? I might, if we were looking at a planet and a satellite or spacecraft in orbit, we might want to use delta R, because the only relevant direction is the distance from the center of the planet. Latitude and longitude are not that important. So X and Y are not important. Only the radial motion is important. So anyways, that's our hope. And what we're going to do, I believe did we get to this sketch? We started this. Okay, so let's go ahead and look at this again. Choose yourself a dot and lightly trace in your velocity vector. And we're going to say that the net force here is not parallel to the velocity, and it is not perpendicular. So you got a little bit of newtons along the trajectory and a little bit of newtons perpendicular to the trajectory. So this would be the net force, for instance, on a car that's accelerating through the turns. Okay, so it enters the turn at 50 miles an hour, and it exits the turn in a different direction at 60 miles an hour. Right? So it's got some speedometer moves, and the direction that it's moving is also changing because it's on a turn. So there's some centripetal and there's some tangential force for this car driving through the curves. So let's refine the force to up here in this, this is my hoped for formula. Instead of using F net, let's use F parallel. The portion of the net force that is parallel to the path. Now let's see if you can follow me on this sketch. I'm going to move this net force vector down here and kind of copy it down here and analyze it down here, simply because I don't want to clutter up my diagram up here on the curve. All right? Now what we're going to do is extract the portion of this vector that's actually parallel to the velocity. That's what we need. Parallel to the velocity means parallel to the path. Tangential to the path means parallel to the velocity. All right, so now the way that we do that is we copy the net force down here, and I made it easy to copy. It's just a straight horizontal vector. Now, I trace in another arrow here so that it's parallel. So this is F parallel, and it's parallel to this velocity vector up here. All right, now, I also trace in a vector here, F perpendicular, that is perpendicular to F parallel, perpendicular to the velocity. And do these two make up the total net force? The answer is yes, in the way that I've drawn them, because If you move F parallel, it forms a right triangle. Right here where my cursor is at the bottom, that's a right angle. And I did this all really, really carefully. So I know that these two sub arrows, F perpendicular and F parallel, they really are at right angles. All right, now I'm going to move F parallel back up to here. But here it is, you know, so. All right, so that's the portion that actually changes the speedometer. So make a note to yourself. F parallel changes the speedometer. F perpendicular does not change the speedometer. It changes the GPS heading. All right, so if you're using your GPS or your Apple Compass application on your iPhone, if you turn your iPhone to different directions, it'll be reflected on the compass, right? And that's what centripetal acceleration, F perpendicular, does. So there's my extraction. So I've extracted F parallel from this. And so here it is down here. This is the portion that changes the speed, all right? And the other portion, well, let me ask you some clicker questions now. All right, you ready? Get your clickers out. And let me change my, hit your refresh key, please. And here's question 2. The parallel component of net force speeds up the Maserati on the track. What does the perpendicular component do for the motion of the Maserati? A, B, C, or D? F perpendicular, the centripetal component. Amber, how does this look? Good. Is it making sense?
Oh, yeah.
Good. 10 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right, let's see what you guys got. Okay. Whoa. Of course, 90% of you got this right. And I did say what the answer was about 2 minutes before the question. So, all right, let's try another one. Or let's keep going. So we've got this F parallel. All right. And just like we defined the impulse, F delta T, now we're going to define something called the work as F parallel times delta S. Or here it is. Now, warning. See, there's another W word. Warning. Capital W. In this context, stands for work. In another context, it might stand for weight force. So be careful as you read, think as you read, and read carefully. And I will not try to ever trick you with ambiguous words. I'll try to make it clear when we're working with weight or when we're working with work. And of course, sometimes you're doing work for a vertical free fall, so you got to use both of them. But if you do, you just got to use them carefully. It's not impossible. Okay, so this is the nice way of expressing our delta U. So F parallel times delta S is going to be delta U, delta of my dynamical quantity called energy. Now, so this is the work, this is the, students, this is the definition of work. F parallel times delta S. And if we were in a trig class or a calculus class, we might use a little bit fancier notation. But this will work for us. Okay, this will do the job. You have to do careful drawing and careful viewing of each sketch and diagram if you don't want to use calculus and trig, but we can do it. Now, the dynamical quantity that corresponds to that, it's not V. It involves V squared, however. And if you do some calculus and a bunch of trig, it works out to be that the quantity that is changing is something called kinetic energy, 1/2 mv squared. So that equal increments of kinetic energy are the things that come in increments of kinetic energy are the things that come in equal sized chunks for equal spatial increments delta y. Now that's on free fall, and in truth that is how you use work in general. So here's the full analog to the impulse formula. Here it is. You know, the impulse was delta P equals F delta T. All right. For in this partner to that, it's delta KE equals F parallel times delta Y. And this is for the free fall example here on the right side of the screen. All right. Now this is something that's fairly easy to calculate. And let me point out to you that if we had done the stopping distance deluxe brain burner using kinetic energy, yeah, we could have done it because we have M and we had V. So kinetic energy number one would have been 1/2 times 0.005 kilograms times the square of 1.7 meters per second. We could have done that. And then kinetic energy 2, what's the kinetic energy at the other endpoint of the deluxe brain burner? 0. Kinetic energy number 2 would be 0, so that's easy. So you can figure out kinetic energies and then delta KE. You can figure that out. And then, hey, what's the force parallel to the trajectory? It's the weight force. That's right. So that would be a minus mg, or a minus 0.005 kilograms times 9.8 meters per second squared. You know, whatever that works out to be. Oh no, sorry, that was the. So this is now we're mixing things up. On the deluxe brain burner, F parallel would be the friction force, which was 0.01 Newton. Remember that? Okay. And in the deluxe brain burner, we were working on the tabletop, so you would want to use delta X. But we had everything. We could have used this. And somebody in discussion, I'm not going to ask for a show of hands, they went strolling through Google and they found some equations that just seemed to work. And they didn't really know why, but it did work to get the right answer. And now you know the rest of the story. Now you know why these work. 1/2 mv squared kinetic energy, F parallel times delta X, F parallel times delta anything, any kind of spatial direction. So let's summarize here. For both trajectories, we partition by a given geometric quantity. On the left, our partition, our tick marks are not mile markers, they're second markers for the basketball falling straight down. So t equals 0 seconds, t equals 1 second, and on down to t equals 3 seconds. The geometric quantity over on the right side, in this four-dimensional space-time, we chose a spatial one. And for a free fall, delta y, negative 18 meters, because it's falling. The dynamical quantity that is the same for each is momentum for this partition, for this bookkeeping scheme over here. Raise your hand if you're an accounting major or if you've had an accounting class. Okay, and if you've been in accounting, you know that there's different ways to keep the books, and there's accounts receivable and accounts payable and all this stuff. And so you got to keep different systems in mind when you're doing the books. And so here's one way of doing the books, temporal. And here's another one over here, spatial. And the dynamical quantity that comes in equal sized bytes on the spatial partition is the energy, the kinetic energy. And what we're going to find out is that there's another way of expressing an energy on a free fall trajectory called gravitational potential energy. So, but in general, delta E is equal on these spatial partitions. Now, I'd like to add in one more thing. The units of energy are the units of kinetic energy, and kinetic energy is 1/2 mv squared. 1/2 mv squared is a kilogram times the square of a speed. All right. So a kilogram times a meter per second, quantity squared. And so that works out to kilogram meter squared per second squared. In the metric system, the units of energy are kilogram meter squared per second squared. And that does have a name. It's called a joule, Joule, after an English scientist named James Prescott Joule, who was a pretty smart guy. It is also equivalent to a Newton meter because it's a force times the displacement. So Newton meter, kilogram meter squared per second squared, or joule. All three of those are valid descriptions for the units of energy, no matter what kind of energy you've got. In a calculation, sometimes you might want to use the basic units, kilograms, meters, and seconds here. And because in a calculation, you might want to do some canceling and stuff. Okay, if you do, this might be better. Sometimes just Newton meters is good enough for the canceling needs you have. But joules always works. Joules is always true for this. Now, I've got some more questions for you. Do you have a question in the back? Okay, just stretching. Good. All right. Clicker time. Let's just go over some of the things that you need to know in order to figure out a free fall kinetic energy situation. What's the formula for the weight force of an object with mass m? And I'm sorry, this looks like that little kid on King of the Hill, doesn't it? Bobby, is that his name, Bobby? "15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Yeah, you guys got that one right. Next question. What is the geometric relationship And I'm sorry, this says figure 3.4. That's figure 3.4 in the old textbook. Sorry about that. Parallel, anti-parallel, slanted, or perpendicular. 10 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Yeah, this is right. And here's, let me see, a few of you got this wrong. Some of you voted perpendicular. No, there's no way perpendicular. If you're in a, read it carefully. It says the object is falling straight down. So it's going like this. It's on it's on the y-axis. And there's no such thing as horizontal gravity. So perpendicular is out. The only thing it could possibly be is either parallel, the same direction, or anti-parallel, opposite directions. But it's going straight down. The trajectory is downward, and so is the force. So these guys are parallel. Next question. The weight force is parallel to the velocity. As a result, see, because these are all the basic questions that you ought to ask yourself when you're analyzing something. You want to know what's happening. Is the speed zero? Is it decreasing? Is the speed perpendicular? Is it increasing? Because the force is parallel to the velocity. So what happens? 15 seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right, let's see what you guys got. Yeah, 90% of you got it right. Good. All right, now I'm going to ask you, I want you to read these carefully. I don't want you to get tripped up. All right, so don't let me catch you napping. Once you get up into orbit, or once you're up in an airplane even, it's easy to drop things back to Earth. Why is that? Now read it very carefully and think. And discuss with your neighbor. Make friends with your neighbor. What is your name again? Catherine? And what's your last name? Cassinese? Cassinese? How do you spell it? All right. Anise. Okay, Cantonese. It's Italian. Excellent. There's two kinds of people in the world. Those who are Italian and those who wish they were. And I'm in the second category, unfortunately. Yeah, but it's an Italian name, so that counts. That counts. 15 seconds. 10, 9, 8, 7, 6, 5, 4, 3. How many voted for? A bunch of you voted for C. Both of these are good. So Add this to your notes. Go ahead. I'm gonna count. I figured out a way to do it. Yeah. Yeah. So, and I did. You know, for last time. And so you guys, I figured out how to give points for both of these. So I'll be doing that. So make a note. If you answered A, make sure you also say in your notes what option C says. And if you're one of the 14 people that answered C, make sure you jot down option A because that's kosher as well. Now I got a bunch more questions here. We're not even close to being done. Let's keep going. You're seated 5 meters up in a tree with a 0.400 kilogram water balloon. See, here's Calvin over here. He's holding on, and he's asleep. Go ahead and answer. The balloon is at rest, but it's ready to drop. "15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Uh-oh. We got some splaining to do. Because a lot of you guys have answered, you're all over the board here with this one. However, this is the answer, and the reason is it's at rest. It hasn't started moving. And hey, you guys, this is an example. This is an example of why I say read carefully. All right? I do not consider this to be a trick question. All right? It's a question that you have to read carefully and think about as you read. All right, let's keep going. You're seated up 5 meters. How much work did it take to get up to that height? Ooh. F parallel times delta y. So we're just talking about the water balloon.
Those two would stop.
30 seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Another one, we got a distribution of answers. All right, let's figure this out. Make some notes. What's the weight force of a water balloon of mass 0.400 kilograms? Weight force is mg. So it's 0.4 times 9.8, and that works out to 3.92 newtons, correct? Somebody verify me on that. Come on, you got your calculators out. 0.4. No, it's it. The water balloon. This is about the water balloon. Yeah, and we're talking about the water balloon. 0.4 times 9.8. Who's got it? What do you got? Okay, so we got, is that what you got? 3.92. So that's the weight force. So you've got to get it up in the, you've got to exert 3.92 newtons of force to move it upward. And the distance that you've got to go is 5 meters. So 5 times 3.92 is 19 point what? 19.6. So here's your answer. Okay. And that's the amount of work. The weight force is 3.92. Delta Y is 5. 3.92 times 5 is 19.6. Question in the back. Yeah, but we're just asking how much work it takes to get the water balloon up there. Yeah, you're doing it for yourself. You're climbing the tree, but the question is about the water balloon. All right. So in other words, how much extra work, instead of just climbing the tree by yourself, how much more work do you have to do to climb the tree with the water balloon? All right. And here's your calculation. So you can jot this down. A lot of you got it incorrect. Make sure to jot this down. And here's the weight force. You've got to exert that much. If you exert that much, you'll get it moving. You get it moving and then keep it moving up at that speed. And then as soon as you get up there, you stop. You put it on the limb or whatever. And that works out to 19.6 joules. 19.6 kilogram meters squared per second squared. 19.6 Newton meters. Another question. You're seated 5 meters up in the tree. How much work will gravity do? You've done 19.6. Now on the way back down, how much does gravity do? You know, you get it up there, then you let it drop. Then at that point, gravity's taken over. You look tired. Join the club. $15 seconds.
Well, the last question was about how much work it takes so how much energy.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Aha! Look at this. We got a distribution on this one too. Now, let's talk it over. If gravity's pulling down 3.92 newtons and it moves, and that's the only net force on it, and it moves 5 meters, and they're both in the same direction, delta KE is 19.6 again. So, somebody just asked me over here, can you explain that again? And the answer is yes. Now, it's gravity that's doing the work. You're not doing the work. You've let go of it, so you don't have contact with it. But gravity still got pull. And the pull force from gravity downward is 3.92 newtons. So if we were keeping track of our numbers, it would be negative 3.92 newtons. Delta Y on the way down is negative 5. So your F parallel times your delta Y is negative 3.92 times negative 5. That equals positive 19.6. Let me ask you another question here. How much kinetic energy will the water balloon have just before impact? It starts with 0. How much will it have just before impact? "15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. You think? Now, let me introduce a concept here. Positional energy. We were talking about 2 positions and 1 change of position, delta Y. Actually 2. A positive delta Y on the way up and a negative delta Y on the way down. But the 2 elevations, 5 meters up and then 0 meters on the ground right before impact, those are the 2 positions. 1 object for 0.400 kilograms. 1 weight force, 3.92 newtons. And make a note, those last 3 questions, the answer was 19.6 each way. And so there's something about 5 meters and a 0.400 kilogram water balloon or object of any type with that mass. Something about it that's defined, 19.6 joules. Girls, please don't talk over me. Okay, excuse me. Right? You guys you're right up in front here. So, anyways, so this idea of position and energy, we have a fancy name for that. It's called gravitational potential energy. All right? And this is our last topic for the day. Let's do a few minutes on this, and we'll probably do a few more minutes on Tuesday. The gravitational potential energy is the energy that you've got if you're up there holding the water balloon. The kinetic energy is 0, but you have the potential to reacquire 19.6 joules of energy when you're up there. And one way to think of it is you've stored energy by you carrying it up the tree. You've stored 19.6 joules of kinetic of energy as gravitational potential energy up there in that tree. All right. So if you think about it as, you know, a plateau or a mountain or something like that, the gravitational potential energy increases if delta, and this is using G equal to positive 9.8. All right, so we don't have a negative sign in there on this one. All right. So if delta Y is positive, the gravitational potential energy increases. All right. And that means you've stored energy in the water balloon, or whatever it is you've brought up to the top of that plateau. On the way down, you lose potential energy, and it's converted into kinetic energy. So you have, if you're up there on the limb, your water balloon has got 19.6 joules of potential energy. Then you let it go, and then just before impact, it's lost all of its potential energy, but it's been transformed into kinetic energy, 19.6 joules. So for every kilogram of mass of the object and for every meter of altitude above the base, you know, whatever you decide your base elevation is, the gravitational potential energy is defined. Another way to think about it is that it is the energy of position. And it's a profound concept. There's actually a lot of calculus in that. But for us, we'll just kind of go with this idea that there's a specific energy. I mean, if you know the mass of your object, and if you know the planet you're on, you have a specific amount of energy associated between two positions, any two positions you might choose. You know, for our tree and our water balloon, it was 19.6 joules. But if you have a smaller water balloon, it'll be a little bit smaller amount of energy. Taller tree, a little bit more energy. But it's always defined. And this formula up here, mg delta y, that is how you define it. And make a note that g in this formula is 9.8 meters per second squared, not negative 9.8 meters per second squared. I am going to give a mega homework over the weekend. Look for it by lunchtime tomorrow. Lots of stopping time and stopping distance brain burners. You're dismissed.